Hi students, welcome back for the next lecture. In the last lecture, we talked about how to determine the concentration of a solution given the amount of solute and solvent, or the amount of solute and solution. In this next lecture, we're going to talk about how we would use that concentration, if we knew it, to determine things about the solution that we might want to know. And so the first of these is to determine the amount of solution that contains a certain amount of solute. And so in this kind of question, the amount of solute would be given, and the amount of solute that you want to have, let's say, and the concentration of solution would be given. And the question would ask how much solution contains this amount of solute. So this is an extremely important question. Let's think about places where this might be important. If you have a patient in a bed who cannot feed themselves, let's say, they will often get a glucose IV. Glucose is blood sugar. And that will give them the right amount of blood sugar for their size of body. Now, clearly, if you have a child who's getting a glucose IV, the amount of sugar that you would put in their blood to sustain their body would be significantly less than if you had a very large, 200-pound man, let's say, with lots of muscle or something, right? Needs lots of calories, lots of blood sugar. So an important question might be, if you're giving someone a solution that contains a certain concentration of blood sugar like you would normally have in blood, how much of how many liters or milliliters of this solution should you give the patient? It will depend on if they're a large person or a small person. This kind of calculation is used to answer that question. Also important for this kind of question is if you're doing a kind of chemical reaction and you want to have a certain amount of the solute involved in your reaction, and this reaction is happening in solutions. Well, the question becomes, what volume of a solution of a particular concentration will you need to use to make your reaction happen and to produce a certain amount of product? And so both of these questions can be answered in this kind of problem. So this one says, how much of a 3.5% mass over volume sodium sulfide solution contains 75 grams of sodium sulfide? And so here we are given this concentration. So we're given the concentration of the solution. We're also given the amount of solute that we want to get, and we're asking how much solution would contain this amount of solute. So our solute is 75 grams of sodium sulfide, and our concentration is 3.5% mass over volume of sodium sulfide. Now, this means that we have 3.5 grams of sodium sulfide in every 100 milliliters of solution. How do I come up with that? Well, this is probably the hardest part of these types of questions. The hardest part is to figure out how do I take what I have here as a concentration and turn that into a conversion factor. And so here we have our data that we're starting with, 75 grams of sodium sulfide. We can tell that's our starting point. That's our data because it is a number and it is a unit. Concentrations are conversion factors. We can tell because it says 3.5% mass over volume. Remember, pers and equals, these things indicate for you a conversion factor, a place where you shouldn't start. Now, the way to take this and to turn it into conversion factor is to read what it says here. It says 3.5%. Percent means per 100. Think of century, right? Century means 100 years. Percent means per 100. So if we're trying to make this into a conversion factor, like we're going to do here, we first write what's in the blue here, 3.5%, 3.5 per 100. So 3.5 goes in the top, 100 goes in the bottom. Then we have to translate what's in green. Okay, first of all, it says mass over volume. So that tells us mass, or grams, is going to go on the top, and volume, or milliliters, is going to go on the bottom. And on the top always goes the solute. So the solute is sodium sulfide. So on the top is going to be grams because it says mass, and solute, sodium sulfide, grams of sodium sulfide. Now on the bottom, for all of these concentration measurements, on the bottom is the amount of the entire solution. Remember, part over whole. The part that is the solute over the entire solution. And because we have volume here, we're going to be measuring that in milliliters. So over milliliters of the entire solution, which I have abbreviated here, SOLN. Okay, so now we have our conversion factor. Now we just have to figure out how we're going to use it. We're going to start by writing out our data, 75 grams of sodium sulfide. And I used this just now. M is grams, volume is milliliters. So to get our amount of solution, we start with our 75 grams. Again, we know to start here because it has number, unit, no pers, no equals. That's where you start. Number, unit, that's your data. 75 grams of sodium sulfide. Just like the old days, right? Just like before when we were using conversion factors. No different. Now, just before, like we were using conversion factors before also, we have to make sure that this unit cancels. So can you tell me what unit's going to go right here? The same unit, right? So that's when we look at the conversion factor we made and we see what number is going to go with grams of sodium sulfide. It's the 3.5. So I'm going to put the 3.5 right there. Then the other side is the milliliters of solution, and that goes on top. And notice our grams of sodium sulfide will cancel, and we're going to get milliliters of solution as our unit. So now that we've set it up, all that's left is to calculate 75 times 100 divide by 3.5 equals. And we get 2,142 about milliliters, but notice our 3.5 has 2 sig figs and our 75 has 2 sig figs. So we're going to round this to 2 sig figs. So where the 2 and the 1 is, since it's a 4, we round down. So we round down to 2,100 milliliters of solution. These zeros are not significant, but we need to write them because we're rounding down. If we round it up, it would be, the nearest 100 would be 2,200. If we're rounding down, the nearest 100 is 2,100, 2,100. So that's where we're rounding right here, 2,100 milliliters of solution. A good thing to do in this kind of question is to do a little reality check to make sure that what you did made sense. So let's think. If we're trying to get how much solution there is, well, the solute is in the solution. So the amount of the solution should be, much larger. This is harder to compare in this question because it's hard to compare grams to milliliters. You're not comparing apples to apples. But if you're comparing the same unit, you should definitely take a look. Is there more of my whole solution than there is solute? Because if there isn't, then you know something went wrong. The solute is a part of the solution, so the solution should always be more in amount than the solute. And here's another example of this type of question. How much of a 0.125 molar potassium hydroxide solution contains 15 grams of potassium hydroxide? So again here, we should take a look at what is it that we have. What is the information we have? Well, we've got the 15 grams of KOH, which is the solute. So our solute is 15 grams of KOH. Our concentration here is 0.125 molars. Molarity, remember, is moles per liter. Per liter. When you hear per, you should think conversion factor. So we've got to make this into a conversion factor. So our concentration is 0.125 moles per liter, or molarities of KOH. So with this one, we don't have a percent. So with the number, we can just write it. We don't write per 100 because we don't have percent. If we had percent, we'd write number per 100, but this is not a percent. Now we have to translate, what does molarity mean? Remember, always on the top is solute. Always on the bottom is entire solution. Molarities is moles per liter. So it's going to be moles of solute over liters of solution. Now we have a conversion factor that we can use. There is an issue though, and that is that because we're using molarities, we have moles per liter. But our data is not given in moles, it's given in grams. So we're going to have to convert that to molarities. How do we convert, to moles rather? How do we convert between grams and moles? The molar mass, right? So to get the molar mass of KOH, so this is going to be 1 potassium, and the potassium is 24.3 grams. I think, let's remind myself here. Let me grab my periodic table. All right, and here's our periodic table. So you can see for magnesium it's 24.3, for hydrogen it's about 1, and for oxygen it's about 16. So going back to our slideshow. So we have 1 times 24.3 plus 1 times 16 plus 1 times 1.0. And so if we add those together, we're going to get a molar mass of 24.3 plus 16 plus 1, and that's going to be KOH, yeah, 41.3. Uh-oh, seems like my math is wrong here. Did I pull the wrong number? I think I pulled magnesium. Yes, okay, that's what it is. Okay, potassium is actually 39.1. All right, so let's get that straight. So this is not 24.3, this is 39.1, so we're going to erase that. Eraser, erase the 24.3. Oh no, it won't erase. Okay, wow. Okay, let's try again. So it's going to be the molar mass for KOH. It's going to be 1 times the mass of the potassium, which was 39.1, not 24.3, and hydrogen, which is 1.0, oxygen, which is 16. So 39.1 grams plus 1 times 16 grams for oxygen plus 1 times 1 gram for hydrogen. And we will get 39.1 plus 16 plus 1 equals 56.1. So the molar mass of potassium hydroxide is 56.1 grams. So before we can use this conversion factor, we've got to convert the grams to moles. Again, like any conversion problem, remember how you determine where to start. Look for the data. What is just number, unit. No equals, no pers. This is not data, moles per liter. That's a conversion factor. This is not data. This is a conversion factor. 1 mole KOH equals 56.1 grams, or 56.1 grams per mole for KOH. This is our data. 15 grams of KOH, number, unit. So we're going to start by writing the 15 grams. Now, when we apply our conversion factor, we need to make sure the unit down here cancels with the unit right here. So we put the grams of KOH. And we want to convert those to moles. And so we're going to put 56.1 grams of KOH right here. And then on the top will be 1 mole of KOH. So 56.1 right here. And the top is 1 mole of KOH. and our grams of KOH cancel. Okay, we're not done though, because what we were supposed to get was how much of the solution will we use. So again, well, first we can calculate this. You can either calculate this and stop here, or you can continue. So 15 divide by 56.1, and we get 0.267 moles of KOH to 3 sig figs. So now we'll carry that down, and we're going to apply the conversion factor we made from the molarity. So we have 0.267 moles of KOH carried down from right here. And again, always whatever unit is here, it better go right down here. So we copy that unit down, and now we see that our conversion factor here with concentration has moles of KOH in it. And the number that goes with that is 0.125. So we're going to put that right there. And the other side is going to be per liters of solution. The moles of KOH cancel, and this liters of solution goes right there. And now let's calculate. 0.267 divide by 0.125 equals, and we get about 2.14 to 3 sig figs, 2.14 liters of solution. Okay, so that's how you do that kind of problem. Next is going to be basically the other side of this. Let's say you're given the concentration and the amount of solution. Then the question is, how much solute was in that solution? So to carry forward my examples with the glucose IV, let's say that you've got a liter here of your glucose IV, and it has a certain concentration to it. And you want to know how many grams of glucose is that person going to get. You could also calculate how many calories, because it's 4 calories per gram of glucose. But what you could figure out is how many grams of glucose is this person going to get in their bloodstream. Again, the amount of grams of glucose that is appropriate for a patient depends on whether they're large or small, right? Likewise, if you are doing a chemical reaction with solutions and you want to know, how much of my solute that was undergoing the reaction was put into this. This is the kind of question you can answer with this. Also, it's used when you're preparing a solution. So let's say you want to make 250 milliliters of a particular solution. You've got to know how much solute you need to dissolve in the volumetric flask or whatever glassware you're using to make the solution. You need to know how much solute to put in there to make the solution. So this is the kind of question we solve when we're trying to figure out how much of the solute we need to weigh out or pour in order to make the solution that we're trying to make. So here's an example. How many grams of sodium iodide are in 145 grams of a 4.50% mass over mass solution? Okay, so first of all, we should identify what do we have here. We've got 145 grams of solution. So this is a little bit tricky. Make sure to read the question carefully and see what it's saying. It's saying 145 grams of a solution that has this concentration. So our amount of solution is 145 grams. And its concentration is 4.50% mass over mass. And this means 4.50 grams of sodium iodide in every 100 grams of solution. The way you get that is you translate this into a conversion factor. And as I said, the hardest part of these problems is taking this concentration and turning it into a conversion factor that you can use. So let's translate this now. We're going to make a conversion factor right here. First, we'll translate the blue part, 4.5%. 4.50% per 100. So we could put 4.50 on the top and 100 on the bottom. 4.50% per 100. Now we need to translate this. Mass over mass concentration. Mass is measured in grams, right? So it's going to be grams over grams. grams of what? Well, it's always the same thing. The top is always the part that's a solute. The bottom is always the entire solution. So it's going to be grams of the solute, which in this case is sodium iodide. So grams because this is mass, and sodium iodide because that's a solute. Solute goes on top. Then grams on the bottom as well because this is mass over mass. Mass is also on the bottom. And we put on the bottom the entire solution because remember, all of these concentrations are amount of solute over amount of the whole solution. And we have units of grams here because we're doing masses. Okay, so again, where do we start? We always start with our data. We don't start here. This is a conversion factor. We can tell percent, mass per mass, or mass over mass. Those are tip-offs that our concentration is a conversion factor. We don't want to start with a conversion factor. We start with number unit, 145 grams of solution. So make sure to read this carefully. It says 145 grams of a blank solution, 145 grams of solution. So I've labeled it there. So now, like every single conversion, we look at the unit here and we make sure that the same unit goes down here. It's going to be grams of solution. Then we look at our conversion factor and see, oh, what number goes with grams of solution? It's 100. So I put the 100 there. Well, then what's on the other side? 4.50 grams of sodium iodide. So that's going to go on top. Our grams of solution cancel, and 4.50 grams of sodium iodide go on top. And now we calculate 145 times 4.5 divide by 100 equals, and we get 6.52 here. Since this is a 5, we're going to round up. And so it will be 6.53, and our unit is grams of sodium iodide. 6.53 grams of sodium iodide. So if you were, notice again, you should always check, do a reality check. Is our amount of solute less than the amount of the entire solution? Yes, the whole solution is 145 grams. That includes the solute, the sodium iodide, and the solvent, the water, all together. Out of that 145 grams, 6.53 grams is sodium iodide. So if we wanted to make this solution, it would take 6.53 grams of sodium iodide to make 145 grams of the solution. Finally, how many grams of lithium chloride are needed to prepare 250 milliliters of 2.5 molar lithium chloride? Okay, so here again we've got molarities, so you've got to remember what molarity means, right? Molarity, what does it mean? Molarity means moles over liters, right? And it's always the same thing on all these concentrations. The top is always the solute, and the bottom is always the entire solution. In this case, is going to be moles of lithium chloride, because that's the solute, over liters of solution in this case. So you do need to know that definition. But remember, the only thing that differs between all these concentration definitions is the way in which the solute and the solution are measured. But it's always solute on top, solution on the bottom. So this says how many grams of lithium chloride I need to prepare 250 milliliters of 2.5 molar lithium chloride. Okay, so first of all, it's asking for grams, but molarity has moles, so we're going to end up having to get moles first. Also, it's moles per liter, so milliliters are not going to be okay here. We're going to have to convert milliliters to liters. So 250 milliliters is 0.25 liters. The way we get that is we have 250 milliliters, and what goes in the bottom? Something with milliliters, and it's 1,000 milliliters that equals 1 liter. So our milliliters cancel here, and we get 0.25 liters. 250 divided by 1,000. That's 0.25. So now we have liters. So now we can use our concentration. But we've got to make sure that our concentration is stated as a conversion factor so we can use it as a conversion factor. So what we're going to do is we're going to write this out. Now this is just a straight number, there's no percentage, so we just write the number 2.5 here. Then we have to write what molarity means. Molarity means moles per liter. Moles of lithium chloride on top and liters of solution on the bottom. Now we have our conversion factor. And this, by the way, is 0.25 liters of solution. So start with your data, 0.25 liters, apply the molarity conversion factor. We're also going to need the molar mass of lithium chloride, okay? This is gotten from 1 mole lithium, 1 mole chlorine. We can go to our periodic table and just add these up. It would be 1 times for lithium, 6.94, plus 1 times for chlorine, 35.45. And we get 42.39 for the molar mass. So the molar mass is 42.39 grams of lithium chloride is 1 mole of lithium chloride. That will get us between moles and grams because molarity is going to get us to moles, but we're asked for grams. So we're going to need that molar mass to go from moles to grams. Again, start with our data here. We got all kinds of numbers. How do you know where to start? We don't start with molarity. That's moles per liter. When you hear per, think conversion factor. Don't want to start there. We have 42.39 grams of lithium chloride is 1 mole equals 1 mole of lithium chloride. Or you can also say that as 42.39 grams per mole. When you see per or equals, think conversion factor. I'm not starting there. Where am I starting? Right here, 0.25 liters, number, unit, 0.25 liters of solution, okay? Now we gotta look at our conversion factors and say which one has liters of solution in it. Molar mass doesn't, it's this one, right? Because what has to go down here? Same unit as here, okay? And so we look at this conversion factor, liters of solution is in the bottom, good. We can write 1 here if we want, we don't have to. So the other side is going to be this top part, 2.5 moles of lithium chloride. So our liters of solution will cancel. Now we have moles of lithium chloride. So we know in our next step, better be what's here is right down here, moles of lithium chloride. And the number that goes with that is 1. And the other side will be this, 42.39 grams of lithium chloride. Moles of lithium chloride cancel. We get grams of lithium chloride here. Now all we have to do is calculate. So 0.25 times 2.5, since it's on the top, and times 42.39 because that is also on the top, and we get this number here. Because the 0.25, notice 250 milliliters here and 2.5, they were both 2 sig figs. So we're going to run around our answer to 2 sig figs. So this is 26. So we'll round to 2 sig figs, 26 grams of lithium chloride right there behind my head a little bit. So if you're going to prepare this solution, we want to make 250 milliliters of it, so we'd use a 250 milliliter volumetric flask. We'd weigh out 26 grams of lithium chloride. We would put it in the flask, dissolve it in a little water, and then fill to the 250 milliliter line and mix. Remember, we do this when we're making a certain volume of solution because the 2 separate volumes, when you combine them, they may change. They won't be the combined volume of each because all the molecules and ions are fitting together in a different way than they did when they were separate. And so that's why when we're making a certain volume of solution, we use the volumetric flask to make that particular volume accurately. Lastly, the last type of calculation we're going to do related to solutions is a dilution calculation. And so in this one, we use a formula or an equation that looks like this. Concentration of the stock solution times volume of the stock solution equals concentration of the dilute solution times volume of the dilute solution. Now, often in your book or in other places, you'll also see this form of the equation. It says M1V1 equals M2V2. That's the same thing, okay? And this is just a little bit more general. So I like to use this way because this one is M is like specifically saying molarity. It's referring to molarity, but not all concentrations are molarities. This equation works whether your concentration is a molarity or not. So that's why I show the equation a little bit differently than you may see it in the book or on a video on YouTube, but it's the same equation. And the reason why it works is because what a dilution is when you make a solution less concentrated by adding solvent. Usually that solvent is water. And we use dilutions all the time. If you're working if you're going to work as a dental hygienist or a dentist or in a doctor's office, dilutions are often made for sterilizing solutions. Or even in restaurants, you may have an iodine solution that you use, and you dilute that in order to make the solution. So this kind of calculation is related to that. And so you can know the exact concentration, whatever the solution is that you're making. Now, usually if you're making the solution, you've been given instructions like, take a capful and put it in a gallon of water or something like that, right? So you don't really have to technically do, some math to figure it out, because someone else did the math for you and told you, oh, if you put the capful in a gallon of water, that'll be the right concentration. But wouldn't it be nice to know how they figured that out? That's what this is all about. And the reason why it works is because you're just adding the solvent. So let's say our solvent is water. And we have here molarity. This is going to be moles 1 over liters 1 times, and volume would be liters 1, let's say. Then we'll have moles 2 over liters 2, a new volume, times liters 2. Okay. Well, in these cases, the liter part cancels. Liters parts cancel, and we get mole 1 equals mole 2. And that is true because this is moles specifically of solute. Moles of solute, moles of solute. And so if you're just adding solvent to the solution, the moles of solute doesn't change. So mole 1 does equal mole 2, right? And so that's why this works. It's because you're not adding any more solute. So a very important thing about using this equation is that it only works when you're doing a dilution. So if you read a problem, let's look at a problem right now. What is the molarity of 15 milliliters when 12 molar of a 12 molar solution when it is diluted to 125 milliliters? Okay. Notice the word diluted. That tells you to use this equation. Okay. Another thing it might say is adding water, adding solvent. That's what diluting is. This is the only time this equation works, okay? It has to be when the moles of your solute did not change. When I show people, CSVS equals CDVD or M1V1 equals M2V2, they want to use this for everything. It's like, oh, I'm going to do my taxes. Better get this, CSVS equals CDVD. No. It's only for one very specific purpose, for dilutions. That's the only time you use this equation. So let's identify what our concentration and volumes are. So our initial volume, our volume of our stock solution, the more concentrated solution that we're using, is 15 milliliters. Its concentration is 12 molars. So concentration of the stock solution is 12 molars. Volume of the stock solution is 15 milliliters. Then we dilute it, we add water or solvent of some kind, and we get a new concentration and a new volume. The new volume is 125 milliliters. That's given right here. We want to know what the new concentration is for our diluted solution. So we do this one. So our equation is CSVS equals CD VD. We're going to plug these in. So the CS, this goes right here. The VS goes right there. And the VD goes right here. And we're going to find CD. So CS here is 12 molars. VS is 15 milliliters. CD is what we're trying to get. And VD is 125 milliliters. So we're trying to solve for CD. So what we do is we divide both sides by 125 milliliters. So that will cancel this 125 milliliters, leaving us only the concentration of the diluted. And then we divide this by 125 milliliters. And notice that our milliliters cancel, and we end up with concentrations of molarities. And this doesn't have to be molarities. It could be any type of concentration unit, as long as you're consistent, so that the units cancel and you get the unit that you want. So now it's time to calculate. So we'll say 12 times 15 divide by 125, and we get 1.44. And we should write this with 2 sig figs, so it will be 1.4. And our unit here is molarities. That's the units that's left. So our result is 1.4 molar. Always good to do a reality check again. Remember, the CD is the concentration of your diluted solution. It should be lower in concentration than your stock solution. Stock solution is the one you keep on the shelf that's more concentrated. So is it in fact less concentrated than the stock solution? Well, the stock solution was 12 molar. The diluted solution was 1.4 molar. So yes, this is a really good thing to do, because in case you get your algebra mixed up, you can fix it later, okay? One more example here. How much water should be added to 16 milliliters of 5 molar Ki to make some 0.25 molar Ki? So notice it says water added. That is dilution. So then you know to use CSVS equals CDVD. We just have to identify what do we have. We've got 16 milliliters of our stock 5 molar solution. So the concentration of our stock solution is 5 molars. We're going to use 16 milliliters of it. So that's our volume of our stock solution. The concentration of the diluted solution that we want is 0.25 molars. So CD is 0.25 molars. What we want to know is what is the volume of that solution. Okay, so we're going to use CSVS equals CDVD. And we know to use this because we have a dilution. Water is being added. So the concentration of the stock solution goes here, volume of the stock solution goes here, concentration of the diluted solution goes here, and what we want is the volume of the diluted solution. So we plug it in, we get 5 molars for the concentration of the stock solution, 16 milliliters for the volume of the stock solution. We get 0.25 molarities here for the concentration of the diluted solution, and the volume of the diluted solution is what we want to find. So now that we have these plugged in, we want to get the volume of the diluted solution by itself. So that means dividing by 0.25 molars on both sides. That cancels the 0.25 molars. And here our molarities will cancel, and we'll end up with units of milliliters. Okay. And so now it's time to calculate. On the left here, we're going to get the volume of diluted solution is 5 times 16 divided by 0.25. And we get 320 milliliters. 320 milliliters. But that's for the whole solution. We were asked how much water should be added. And we started with 16 milliliters of solution. So we take the 320 milliliters that we did of the solution we made, we subtract the 16 milliliters of stock solution that we started with, and we get the 304 milliliters of water should be added to make this solution, approximately. Okay. So make sure to read the question carefully too. Yes, the dilute solution was 320 milliliters in volume, but we started with 16 milliliters of stock solution. So we added 304 milliliters of water to make that solution. And so those are the calculations that are involved in concentrations. So now you can answer questions like, like I was talking about before, how much, glucose is in a liter of glucose blood sugar IV, or how much there's like maybe a little injection of sodium chloride saline solution. How many grams of sodium chloride are dissolved in that saline solution? Saline solution is salt water, sodium chloride in water. And so those kinds of important questions you can answer with these skills that you've learned here. In the next lecture, I'm going to be talking about some qualitative aspects of heterogeneous solutions. And that will be important because your bloodstream, for example, is a heterogeneous solution. And depending on the concentrations of what is put into your bloodstream, that can have an impact on the components of that solution. And also it's just really important for a lot of biological applications to talk about relative concentrations of things in heterogeneous solutions for biological organisms. Also, of course, as a scientist, this will be important to you as well. So I'll see you in that next lecture.